My name is Nick Beim. I am a partner at Venrock, and I have spent much of the last 5 years trying to figure out the economics of artificial intelligence, and I have to confess, I am not yet there. I'm still working on it. But thankfully, our speaker today, Ajay Agrawal, has spent a lot of time on the subject, has published academic papers on the subject, has written a book on the subject that he's going to talk about today. I've had the opportunity to work with Ajay on multiple projects, and I think what's particularly interesting about him is he's both a distinguished academic and a successful serial entrepreneur in the field of artificial intelligence. So on the academic side, he is the Peter Munk Professor. He's a Peter Munk Professor of Entrepreneurship at the University of Toronto, where he focuses on the economics of artificial intelligence. He's also a research associate at the National Bureau of Economic Research in Boston. And on the entrepreneurial front, he's founded 3 entities, all associated with artificial intelligence, that have been really interesting. One of them is about to open up operations in New York. So the first, the one that's going to open up operations in New York, is called Creative Destruction Lab. And I have been an advisor to the organization. It started in Toronto. It is an accelerator that is home to 150 AI-driven startups, which, for those who haven't been keeping track, is the largest concentration on the planet. So a really interesting achievement. And as I said, they're going to be expanding operations into New York. The second is Next AI, which is a program for young AI entrepreneurs in Canada. And the third is Kindred, which is a startup that builds machines that with human-like intelligence, and was recently named to the MIT Tech Review's 50 Smartest Companies and to CB Insight's AI 100. And due in part to his work on AI, in 2017, the Globe and Mail, which is a national Canadian newspaper, named Ajay one of the 50 most powerful people in Canadian business. And today he's going to talk about his new book, Prediction Machines, The Simple Economics of Artificial Intelligence. This will all be simple and easily understandable to everyone by the end of the talk. And it was published worldwide this week by Harvard Business Review Press. So here's how the logistics will work today. Ajay will speak for about an hour. Then we'll have about 15 minutes of Q&A. And then we'll have coffee and discussion for everyone together outside afterwards. And as you probably saw on the way in, there's a big stack of books in the back. Feel free to take one on your way out. And with that as background, please join me in welcoming Ajay Agrawal.
Great. Okay, thanks very much, Nick. Thank you. And thanks for hosting this. And the folks at AppNexus, thank you very much for hosting me here. And I don't know if Kelly's here, but she coordinated all my logistics, and so I'd like to thank her. And also thanks to Jim Levine and Beth Fisher, who are our literary agents and helped us bring this book to fruition. So thank you for being here. Just so I can calibrate, how many people here have an AI company? I suspect there's a few, okay, that are entrepreneurs. And then how, just in terms of familiarity, if you had to just stand up now, or who would feel comfortable standing up and in a few sentences, in their own words, defining what AI is? Okay, 3 or 4. And if those at organizations, if you were to characterize how you where you would place your organization in terms of having an AI strategy, imagine 3 categories. Category 1 is we're fully prepared. We have an AI strategy in the works. Category 1. Category 2 is we're putting a team together to start working on that. And category 3 is we have no idea where to start. Those that are in category 1, just by show of hands. Okay, 1, 2, 3 people. Category 2, the sort of medium category. Okay, and the category 3 people. All right. Okay, so hopefully by the end of this, at least for the first question, which is define AI, everybody will leave the room feeling very comfortable that you could define it for anybody. And also most people hopefully will feel comfortable in the second one, that you have at least a sense of where to start. Okay, so I don't need to tell this audience, you've all self-selected to be here, that AI is, I think the reason there's a fair amount of enthusiasm about this technology is that it's what economists would call a GPT, a general purpose technology, that it seems to be everywhere. It's now hard to find any market where there's not some AI applications that are rolling in to advance the productivity of whatever they're doing. At the same time, there's a fair amount of just angst, people trying to figure out what it is and what the implications are, how they can deploy it, and what that means for humans. And so my role this morning, and what we try to accomplish with the book, is to remove some of this anxiety by way of providing some clarity. How can we think of AI, particularly those people who don't have a computer science background? And to do that, what we do is we take a topic that is really the domain of computer science and put a layer of a different lens on it from a discipline that we often don't associate with clarity, and that's economics. And so by putting an economics layer on top of a computer science background, in this case, we think we can provide a fair amount of just insight into how we can think about development of AI. So my background is I'm an applied economics professor at the University of Toronto, and I teach at the business school. And the reason that this matters is because 2 blocks down from my building is the computer science building. And due to some serendipity, and in fact a hiring mistake 25 years ago, Toronto became really the epicenter of the recent renaissance in AI. And so today, several of the most powerful industrial AI groups in the world are headed by people who were 10 years ago at Toronto. So the person who originally led the AI group at Facebook here in New York was 10 years ago at University of Toronto. The person who leads AI research at Apple in Cupertino 10 years ago, University of Toronto. The person who leads the AI research for Elon Musk, OpenAI, the billion-dollar OpenAI Institute, 10 years ago, University of Toronto. And so the reason that that's relevant is that I am the founder of a program at Toronto that Nick mentions opening up here under the leadership of Professor Deepak Hegde, who's here, called the Creative Destruction Lab. And the focus of the lab is to transition science projects into massively scalable companies. And so about 5 years ago, what started as a trickle and turned into a flood was graduate students coming out of this lab, this computer science lab. The companies are coming from around the world to Creative Destruction Lab. But out of this particular lab right on our campus, the first one that came was a graduate student who said, I'm going to use this new technique for predicting which molecules will most efficiently bind with which proteins for the purpose of drug discovery. And then right after him, his name was Abe Heifetz, right after him, another one came and said, I'm going to use this technology for predicting which credit card transactions are fraudulent versus legitimate. And then another one came and said, I'm going to use this technology to look at medical images and predict which tumors are benign versus malignant. And then another one came and said, I'm going to use this technology to predict which automobiles have defects before they roll off the production line, and so on. And so as we were sitting in the lab, myself and 2 of my colleagues, Avi Goldfarb and Joshua Gans, it didn't take a rocket scientist to figure out there's something unusual coming out of this computer science department. That the same underlying technique, which we now refer to as deep learning and reinforcement learning, the same underlying technique is being used to give a material lift to this very wide set of applications. And so after a while, we just started to document what we were seeing. And then we compiled our notes into what are the general lessons to be learned that are applicable across all of these different cases. And that resulted in this book that hit the bookstores yesterday. And so what I'm going to do now is just give you some of the key points from the book. Okay, so I don't need to say to this audience that a lot of people are feeling that today in AI feels a lot like 1995 felt with the internet. Heidi, I wonder if we can just, I'm getting a little bit of echo. So it feels a lot like 1995 felt with the internet. So most people will remember that 1995 was a real transition year for the internet. So we had the internet for at least a couple of decades before 95, mostly used by the military and academics, BitNet, ARPANET, and so on. And it was growing over time. And then in 1995, there was a big jump. That was the year that Bill Gates wrote his famous Internet Tidal Wave email. Microsoft launched Windows 95. NSFNet was decommissioned, which removed the last barriers to carrying commercial traffic on the web. And in August of that year, Netscape went public. So a $3 billion IPO for a company that really had generated almost no profits. And right after this, so 96, early 97, the language around the internet started to change. And we stopped referring to the internet as a new technology and instead began referring to it as a new economy. And the point here was that it had permeated so many parts of our lives that we stopped thinking of it as a technology and started thinking of it as a different way of interacting in the economy. And so CEOs and journalists and entrepreneurs and investors, politicians, all started referring to this as a new economy. Everybody referring to a new economy except for one group of people, and that was economists. And economists said, wait a minute, this isn't a new economy. This is exactly the same economy we've always had. In fact, we won't have to change a single word or a single page in an economics textbook. All the underlying economic models still hold. Everything's still driven by supply and demand, production and consumption, prices and costs. It's all the same. The only thing that's changed is that the relative costs of a few key inputs have fallen dramatically. The cost of digitally distributing goods and services, the cost of search, the cost of communication. And that's the way that economists view the world. The thing that economists are quite good at is to take a new technology and strip all the fun and wizardry out of it and resolve a tech down to a single question. And the question is, what does this reduce the cost of? And surprisingly, that often gives us some great insights. So for example, the heart of Silicon Valley, of course, is the semiconductor industry. And if you ask a computer scientist or an electrical engineer, can you please describe to me the rise of the semiconductor industry? In their heads, they'll have an image like this, and they will describe to you the underlying science behind cramming more transistors onto a chip. So they'll explain to you, the number of transistors on a chip doubling every 18 months and Moore's law and the implications of Moore's law. That's what the technologist will explain to you. Whereas if you were to ask the same question to an economist, can you describe to me the rise of the semiconductor industry? This isn't the image they'll have in their head. They'll have this image. And the reason that economists will say that semiconductors are so foundational, while there's many things happening in the Bay, that semiconductors are the engine of the innovation economy in Silicon Valley, it's because the thing for which the cost fell was such a foundational input. And in the case of semiconductors, that thing was arithmetic. So economists think of semiconductors as the rise of semiconductors as a drop in the cost of arithmetic. And how many people saw the film Hidden Figures? Okay, does anybody remember what the job title of the women who were the protagonists in that film? Computers, right. So they were called computers because what they did was they came to work and they computed. And there's a scene in the film where they roll in the big machine, the big new computer, and everyone's trying to figure out what that means for them. Okay, so when the cost of something falls, three important things happen. And by understanding these three things, we gain great insight into figuring out how this will affect the economy. So we start off by going back to your Economics 101, and just the very first thing everybody learns is downward sloping demand curves. And the downward sloping demand curves, the key insight is that when something gets cheaper, we use more of it. And so, for example, things for which we already used arithmetic, things like the types of calculations that they were doing at NASA in the film, and the Census Bureau and the military, where we were using a lot of arithmetic, we just started using a lot more. And so it was better, faster, cheaper arithmetic. We started doing more of it. So the cost falls, we use more of it. We also, and this is where things become interesting, is we use more of it not just for things that were traditionally arithmetic problems, but we start taking things that weren't arithmetic problems and convert them into arithmetic problems to take advantage of the new cheap arithmetic. An example of that is photography. Photography used to be a chemistry problem. We solved photography with chemistry and made film. But as arithmetic became cheap, we transitioned to an arithmetic-based solution to photography, and music, and communication, and banking. One thing after another, we transitioned to an arithmetic-based solution. Okay, now on to AI. If we were to ask a technologist, an engineer or computer scientist, can you please describe to me the rise of AI? What they would describe to you is the rise of the science and the statistics underlying neural networks. And they would talk to you about inputs and outputs and the nodes of the network and the links between the nodes and the weights of those links. They would explain to you a development of a statistical process called backpropagation and so on. But if you were to instead ask an economist, can you please describe to me the rise of AI? They wouldn't have this image in their head. They would have this image. Now, at this point, people will be thinking, wait a minute, economists are reasonably single-minded. They see everything the same. At some level, that's true. But this is the key to understanding why economists think of AI as in a category of its own. So if you go to CES, the Consumer Electronics Show in Las Vegas, and you see a rainbow of new technologies in robotics and drones and virtual reality and so on, you see so many different areas of tech. And you say, look, there's so many things. Why is AI so special? The reason economists will say AI is in a different category than all those other things. And the reason is because the thing for which the cost falls is a foundational input into such a wide range of activities that we conduct. And of course, in the case of AI, that thing's prediction. So we can think of AI as the rise of AI as a drop in the cost of prediction. And what I find is just a useful exercise is anytime you're reading a magazine article or something about AI, replace it as you're reading it with the words cheap prediction. And the article will suddenly seem less magical and more practical. And you can sort of make sense of exactly what are they trying to do. So first of all, how do we define prediction here? Prediction we define as taking information you have to generate information you don't have. So that includes what most people would traditionally call prediction, like demand forecasting. So taking, the last 5 years of sales to predict or forecast next quarter sales. So that's an obvious form of prediction. But a less obvious form that we would still call prediction is something like classification. So, for example, I mentioned looking at a medical image. That's the information we have, or the pixels in the image. And the information we don't have is whether the tumor we're looking at is benign or malignant. And so the AI generating that classification, we would call prediction. Okay, so prediction is taking information you have to generate information you don't have. So here we go. We have a substantive drop, a plummeting in the cost of prediction. What does that mean? What are the implications for business and for society? Okay, so 3 big implications. Implication number 1 is that downward sloping demand curves, when the cost of something falls, we'll use more of it. So that means, first of all, in all the things where we currently use prediction, like demand forecasting, supply chain management, insurance. All of these things will simply use the new super powerful prediction, better, faster, cheaper. So we'll just start seeing AIs coming in and replacing the traditional statistical techniques we use for doing prediction. At the same time, we'll also, and this is where it'll become interesting, this is where, in my view, AI on the business side, separate from the computer science side, becomes an art more than a science, which is we will start converting non-prediction problems into prediction problems. So we'll start using more prediction by converting things into prediction problems. An example of that, so just like we did in arithmetic, an example of that is driving. This is the one that everyone's most familiar with. So driving, we've had autonomous vehicles for a long time, 30 or so years depending on how you count. But we always deployed our autonomous vehicles in a controlled setting, so a factory or a warehouse. And the way we did it, simplified version, is that an engineer would have the floor plans of, let's say, a factory or warehouse, and they would program a robot to move around the factory floor. And then they'd give the robot a bit of intelligence. They'd put a camera on the front, and then they would tell the robot, if somebody walks in front, then stop. If the shelf is empty, then move to the next shelf. If, then. If, then. So a series of logic, of rules that gave the robot some intelligence. The problem was you could never take that robot out of the controlled environment and put it in an uncontrolled environment because there were too many ifs. In fact, there's an infinite number of ifs. If it's dark, if it's raining, if a child runs up to the edge of the road, if a car comes with oncoming car with a left turn blinker on, if, and all the ifs are interacted. And because there's an infinite number of ifs in an uncontrolled environment, as recently as 6 years ago, the experts in the field were saying, we will not have an autonomous car on a city street in our lifetime because we simply cannot program all the ifs. Until people in the machine learning field reframe the problem and said, rather than programming an infinite number of ifs, what if we change the problem to instead making one prediction? And that prediction would be, what would a good human driver do? And so the simplified version of how an autonomous vehicle works, at least a way to think about it, is imagine a car, and in the car you put a human. And put the human in the driver's seat, and imagine putting an AI in the passenger seat. And so what we do is we tell the human who's sitting in the car, drive. Just drive. Drive for 1,000,000 miles. And so the human sits in the car and starts to drive. And as they're driving, they have data coming in through the cameras on the front of their head and in the microphones on the side of their head. And as the data comes in, we process the data with our monkey brains, and then we take an action. And the actions are very simple. It's a very small set of thens. We can turn left, we can turn right, we can brake, and we can accelerate. That's it. We have many, many ifs coming in, and we have a very small number of thens. Okay, now on to the AI. So imagine the AI is sitting beside the human. The AI doesn't have its own eyes or ears, so we give it its own sensory inputs, cameras, radar, LiDAR around the car. And the way to think about it is imagine the ifs are coming in, the data's flowing in as you're driving, and every fraction of a second, the AI is looking over and trying to predict what will the human driver do in the next second. And so in the beginning, the AI is not a very good predictor. They have big confidence intervals on their predictions, meaning they're not very accurate. And so they say, I think she's going to turn left. I think she's going to go straight. I think she's going to brake. And then something happens. Either she turns left or she doesn't turn left. And every time they make a prediction, and then they get to, the AI observes what the human driver does. If they were right, they double down on their model. If they're wrong, they update their model. And then they make a different prediction, potentially the next time. Okay, and so as they're driving, in the beginning, the AI's confidence intervals are very wide. They're making a lot of mistakes, but as they drive and they learn and they correct their mistakes, the confidence intervals get smaller, 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 until at some point, the AI is such a good predictor of what the human driver would do that we say the AI can just do it itself. And so the AI has become a prediction machine for driving. And that is really where I think a lot of the enthusiasm is. It's converting problems that weren't traditionally prediction problems into prediction problems to take advantage of the new cheap prediction. So driving is an obvious one, but we've done it in so many other areas. Translation. Translation used to be a rules-based problem. We had linguists who were experts in the rules of translation and all the exceptions, and they would do translations. But we've converted translation into a prediction problem. And now, for those of you who, for example, used Google Translate, even between a year ago and today, the improvement is significant, and it feels like it's not too far away that we'll have a commercial-grade translator that's based entirely on prediction rather than rules. Okay, at our lab, a creative destruction lab, so Nick mentioned that this is where we have all these AI companies that have come in the last 5 years, and as far as we know, the Creative Destruction Lab is now home to the greatest concentration of AI startups of any program on Earth. They're coming in from all over the place, and these AI companies, each one is working on solving a prediction problem. And now we're having a lot of corporates, large companies come in who want to better understand AI. And an interesting group are people who are heads of HR. And so the common conversation we have is a head of HR of this large corporation or that corporation will fly to Toronto and they'll say, we're trying to learn more about AI. I need to know for recruiting, what types of skills should we recruit for? How should we train our staff in order to prepare them for AI? We need to know for the other parts of our company, the sales department, the manufacturing compartment, the design compartment, but not for my department because I work in HR. HR is a very human business. That's what they say to us. HR is very human, but for the other parts of the company, we need to learn about AI for recruiting. Now, most of you know where this is going. One by one, AI companies are transforming the HR process into a series of predictions. So what do HR people do? Well, the very first thing they do is hire. They recruit. Recruiting is effectively now a prediction problem. We get a series of resumes and cover letters and interview transcripts, and then we predict from a set of applicants which ones will be best for the job. Once we've hired people, the next thing we do is promotion. What's promotion? A prediction problem. We have a set of people working in the company, and we need to predict of those people who would be best in the next level up. Then our next issue is retention. Let's say we're at a 5,000 or 10,000 person organization. We need to retain our best people. Well, what's that? It's a prediction problem. We need to predict which of our stars are most likely to leave and what types of incentives would be most effective to keep them, and so on. One by one, these roles are being converted into prediction problems so that AIs can tackle them. Okay, so item number one, when the cost of something falls, we use more of it. And we use more of it for both traditional things, and we also convert new things, in this case, into prediction problems to take advantage of the better, cheaper, faster prediction. Here's the number 2 and number 3. When the cost of something falls, it affects the value of other stuff. In economics language, we call that cross-price elasticity. Basically what it means is you can think of things as being related to the focal thing as complements or substitutes. So think of coffee. If the cost of coffee were to fall, the complements to coffee, the things we use with coffee, like cream and sugar, the value of those things would go up. Because if the cost of coffee falls, we'll start consuming more coffee, and because we're consuming more coffee, we'll also consume more cream and sugar, and therefore the value of cream and sugar will go up. Or if the cost of golf clubs falls, the value of golf balls goes up. All right. And so those are complements. The value of complements go up. The value of substitutes go down. So in the case of if the cost of coffee falls, at the margin, some people switch from tea to coffee, the value of tea falls because the demand for tea diminishes. Tea is a substitute, cream and sugar are complements. Now, how does that work in AI? We can take any task and break it down into these components. Any task. And so it doesn't matter what part of the organization you work in, there'll be a series of tasks that you do, and every task can be broken down into these bits. So an example, let's say that as I'm giving this talk right now, I bang my knee on the lectern, and 3 days from now, my knee is really sore. And so I go to the doc, and I tell her my knee's sore, and so she says, okay, she asks me a bunch of questions, maybe she sends me for an x-ray. That's input. She's collecting input. Then she makes a prediction. And her prediction might be, I think with 90% probability, you've bruised your knee. With 10% probability, there's a hairline fracture. Then she applies judgment. And her judgment is, the way to think about it is, how costly would it be for this patient if they actually have a bruise, but I mistakenly treat it as a fracture, versus if they actually have a fracture and I mistakenly treat it as a bruise. That's her judgment. She's taking all the things that she knows about me and is trying to figure out the cost of a mistake. That's judgment. Then she takes an action. So her action might be saying, okay, I've decided, I think it's a bruise, I'm going to treat it as a bruise, put some ice on it, raise your leg, and if it's still hurting in a week, come back and see me. That's the action. Then there's an outcome. The outcome would be, a week later, let's say my knee's better, I'm good to go, and so we've learned that she was right, and that becomes feedback data, which we use, that in this case strengthens the model. Or let's say it was wrong, a week later my leg is worse, and then that's feedback data, and we update and change the model for the next time. Okay, so any task we can break into these components, and we find this very useful for designing strategy around AI, and for thinking through what are the implications for jobs and the economy and so on. Here's how. If you look at this diagram, it's very clear what is the substitute for machine intelligence. So as machine intelligence increases, as the cost of machine prediction falls, what's the substitute for machine prediction? It's the box in the middle, human prediction. The value of human prediction will fall as the capability of machine prediction increases. So we are quite poor predictors. We're slow, we're noisy, we have all sorts of systematic biases in our prediction. It's been very well documented in books like Danny Kahneman's Thinking Fast and Slow, Ariely's Predictably Irrational. All these things document how terrible humans are at making predictions. But we still make them all the time. And so as the capabilities of machine prediction increase, the cost of machine prediction falls, the value of human prediction will plunge. So our human prediction capabilities become less and less valuable because the machines can do it so much better, faster, cheaper. And that's the part I think the press has been fascinated with, and that's led to a mischaracterization of a complete wiping out of the role of humans. What they miss when they focus on that are all the other boxes. The other boxes are the complements. They're the cream and sugar. They're the things that will increase in value as the price of machine prediction falls. The one that the press has talked about is the first one, input. So how many people have heard the phrase, data is the new oil? Okay, most people. That is effectively talking about the first box, the input. We've always had data. That data we've had, a lot of that data we've had for a long time. Why is it the new oil? What makes it new? What makes it new is it's way more valuable. The same data is way more valuable today than it was 10 years ago. Why? Because the cost of prediction has fallen, and so the value of the data has gone way up. Okay? It's a complement. The data is a complement. It's more valuable now because we can do more things with it because prediction is better, faster, cheaper. So the press has done a good job of talking about the input box, but the press has not done a good job so far of describing the other bits. Human judgment. AIs do prediction. They don't do judgment. They don't know what to do with their predictions. We have to give them guidance on what to do with the predictions. We decide. That's judgment. So, for example, the doctor who's deciding what's the cost of a mistake, she's using her judgment. And so what's interesting is that we're always applying our judgment, but the value of our human judgment goes up as the cost of prediction goes down. As we start getting better, faster, cheaper predictions, as the fidelity of our predictions increase, of machine predictions increase, the value of our human judgment goes up because we're applying our judgment to much better predictions. Okay, the next one is action. That predictions are generally used to inform an action. What action should we take? Companies, operating companies own very often now, like the incumbents, they own the action. That's a valuable asset. It's not just the input, the data that matters. It's not just data is the new oil. Your actions are valuable because now you'll be able to take better actions because you're basing those actions on higher fidelity predictions. So in our lab, where we have all these AI companies, one of the issues is that they build and sell predictions, but they don't own the actions. And so they have to sell their predictions to someone who does own the actions, because without the actions, their predictions are worthless. So actions are a complement. The value of actions goes up. Where we have the most amount of negotiations with all the AI startups, a lot of them who are selling their predictions to larger enterprises, is on feedback. That's the gold dust. When we take an action, we find out later whether that action was a good one or a bad one. And that's how we learn to update the AI. So all our AI startups that are trying to license their predictions output, sell their predictions to enterprises, are all trying to get their hands on the feedback data. And the companies, some of them realize, some of them don't, that that's the gold dust. That data is to some extent much more valuable than this data. This data, using the oil analogy, you use it and you burn it, it's gone. In other words, you use it to train your AI the first time. But once you've trained your AI, there's a few caveats here, but the main one is, sort of broad way to think of it, is you use it to train your model, and then it's done, the value's gone. The ongoing value comes from the feedback data that allows the AI to continue to learn. Okay, so the key points here is in thinking about strategy and thinking about the implications of jobs, is that the value of human prediction falls, but the value of all these complementary assets go up. And a useful way to think about this, an example, is think about when spreadsheets rolled into town and accountants. The accountants originally, you could think of them as having two broad skill sets. One of them was that they would type in the numbers and add, and so they had we valued their ability to type fast and to add fast. And then the second skill they had was to ask good questions. So let's say they were doing a model to estimate the present value of some asset, and then they might ask a good question by saying, well, what would happen if interest rates went up by 1%? Or what would happen if sales went up by 4% in the fourth quarter? And so they would ask a question, but then they'd have to, as soon as they ask the question, they have to start at the beginning and retype everything and re-add up the whole set of numbers in order to test that new scenario. When spreadsheets rolled into town, the value of the human ability to type fast and add fast went down because the machine could now do that. But the value of being able to ask good questions of your data went up because it became much quicker and easier to ask a question. So if you were good at asking questions of, doing scenario analysis, the value of you as an accountant went up. So if you were an accountant where your key skill was asking good questions, your value went up. If your key skill was adding fast, your value went down. Okay. So if AI is just prediction, if the current renaissance in AI is really all about lowering the cost of prediction, and it's not Dolores from Westworld or C-3PO, then why is there so much fuss? Why is there so much fuss about AI if all it is a prediction tool? The answer is because prediction is a key input to decision-making, and decision-making is everywhere. It is riddled throughout our business lives and our personal lives. And so this is the structure of the book. It's in 5 sections. In section 1, we talk about prediction. We explain what's so interesting about the new method of prediction compared to traditional prediction tools and statistical techniques. Section 2 is about decision-making. And while AI is new, decision theory is old. We have about 50 years of a well-developed decision theory. And so we can actually have a pretty good sense of what happens when we take this new prediction technology and put it inside a process of decision-making that we understand quite well, that has been studied for a long time. So that's section 2. You can think of them as the 2 academic parts of the book. Then we get into the practical parts. Section 3 is on tools, which is the actual building of AI tools. And in that section, I'm not going to, I guess I'll just give it a couple minutes on the tools, is the basic idea here is that we can take any workflow. So a workflow is inside an organization, turning an input into an output. That's a workflow. So you can think of a line of business as a workflow. And we take the workflow and we break it down into tasks, and every task is predicated on a decision or a couple of decisions, and AIs do tasks. They don't do workflows, they don't do jobs, they do tasks that are predicated on a decision. So an example, this is an article many people here would have read by at the time, the CFO of Goldman, and in this article, they open up with this dramatic statement by saying, at its height back in 2000, the US cash equities trading desk at Goldman employed 600 traders. Today, there are just 2 left. Okay, that's the dramatic opening. But later down in the article, they have a more interesting sentence. So they talk about now they're working on more complex areas of trading, like currencies and credit. They're trying to emulate as closely as possible. You can replace that with predict what a human trader would do. Goldman has already mapped 146 steps taken in any IPO. Okay, so the idea here is that they've taken the IPO workflow and broken it into 146 different tasks. And so what we do when we are building AIs is we take each task and we estimate the return on investment, the ROI, for building an AI to do that particular task. And then the way to think about it is we just stack rank order the tasks. Which ones have the highest ROI for building or buying an AI? We start at the top and work our way down. So right now, this is not for the Googles and Facebooks who are already well into this, but the 99.9% of other organizations who are just getting into AI, this is an approach we use to getting started. We map out the tasks, we rank them, and then we start at the top and start working our way down. Okay, and so sometimes there are companies that come to the Creative Destruction Lab, large companies, and say, hey, we've got 3 AI pilots at the company. Are we at the frontier of AI? And so just to calibrate, Google now has almost 2,000 AI tools under development. And they're probably the high water mark, or possibly Baidu. So we've built this thing, it's in the book, it's called the AI Canvas, and we have found this a very useful tool for getting companies started with AIs. And so what we often do is, let's say there'll be 50 people in an offsite, and they come from all parts of the company. They're usually vice president level and above, and they sit in tables of 4. And halfway through the day, they go into these breakouts, and they fill out this page. And very often there are the whole set of people, not a single person in the room has ever written a line of code. So they don't have to have any technical background. But they simply go through their workflows, and they pick out tasks, and they say, okay, what if we built a prediction machine, and this is the prediction, so they specify the prediction, and they say, with that prediction, here's the human judgment that would be applied to the prediction, this is the action that the prediction motivates, and then here's the outcome that results from that. And then the training data, the data we use to run the AI, and the feedback so the AI can learn. And so people with no technical background fill out this thing, and by the end of the day, we have an organization has a list of 20 AIs that have been just designed at a very conceptual level by senior people in the organization. And we found a useful way to help them get started and just create a map of the organization of where they can start building AIs. Okay, so the last thing I'm going to talk about is strategy. So most of the time, when we build AIs, we are building tools that are very specific, and their role is to just make a process more efficient in the service of executing against the organization's strategy. So just like Microsoft Word or Excel, an AI is a tool to make you more productive executing against a given strategy. But occasionally, an AI can so fundamentally transform the economics of a process that they change the strategy itself. So this is what the popular press often refers to as disruption. And so what I'm going to show you now is the process that we use for helping to give us guidance on which AIs might lead to a disruption, a strategy change for the organization. Our view is that the main thing when we're going through what I'm about to show you is to develop a thesis on time. So in other words, the thinking about the time it will take for what I'm about to describe to happen will very much influence the investment decisions made today. In other words, whether something will happen in 3 years or 10 years has very different implications for the investments you make today. So if I were giving this lecture even 2 years ago, most of what I'm about to say would be if. You know, if this were to happen, then wouldn't this be interesting? Or if that were to happen, then imagine the possibilities. Over the last 24 months, as most people in this room probably know already, we've had way too many proof of concepts to be thinking about this as an if anymore. In other words, we've had these in vision, so you can think of that as basically machines being able to see, giving them eyes. In natural language processing, so allowing them to comprehend words and language, effectively predict what those characters are trying to communicate. In motion control, robotics, being able to do things. So this is no longer a discussion of if, it is a discussion of when. So we know it's possible. Now it's all about turning the crank and getting those predictions up to commercial grade levels of accuracy. So we are in most cases now in the turning the crank mode, as opposed to in the wondering if it's even feasible. So here's the thought experiment. We use a process we call science fictioning. But it's not science fictioning in the sense that you can sort of sit behind a desk in blue sky and think AIs can do anything. It's a very specific kind of science fictioning. The thought experiment is imagine a radio knob, and you can turn the radio knob. But instead of turning up the volume, when you turn the knob, you're turning up the prediction accuracy of an AI. So that's the only thing, the only parameter you're allowed to move, is turning up the dial on the prediction accuracy. So here's the thought experiment. Everybody's been shopping on Amazon, so we use this as an example that everybody will be able to imagine. And when you shop on Amazon, you are immediately introduced to an AI. That's the recommendation engine at Amazon where they recommend, we think you might want to buy this, or you might want to buy that. And right now, for myself and my co-authors, on average, that recommendation engine is about 5% correct. Meaning out of every 20 things it shows us, we end up buying one of them. Which 5% accuracy might sound lousy, but it's not too bad when you think that there's millions of things in the Amazon catalog, and it's going out and pulling out 20 of them, showing them to us, and we're buying one. So, as you know, we go into Amazon, the recommendation engine shows us some stuff, and we shop around, and we see things we like, we put it in our basket, we pay for it, and then the order arrives on somebody's tablet in the fulfillment center at Amazon, and the Kiva robots are moving around, and they bring the stuff up to the human pulls it out of the shelf and puts it in the box, puts a label on the box, ships it to your house, it arrives at your door, and you bring it inside, and that's how you shop at Amazon. And we can summarize that by calling that method shopping, then shipping. You shop for the stuff, and then Amazon ships it to you. Okay, so here's now the thought experiment. Is imagine that recommendation engine, which most of us just breeze by. We don't put a lot of thought into it when we see it on the website. Imagine that, when we don't have to imagine, this is just happening, is every day at Amazon, the people in the machine learning group are working on turning the knob. And so let's say right now that knob is at a 2 out of 10. And they are working, they're improving their algorithms, they are testing some different approaches, they are acquiring data assets like buying Whole Foods so they can learn more about how you and I shop offline. Each time they do that, they're cranking the knob. So maybe they're 2, maybe they'll get it up to a 3, and then a 4, and then a 5. And they are working entirely focused on turning the knob, increasing the prediction accuracy. As they increase the accuracy, they don't have to get up to spinal tap levels. Maybe it's a 6 out of 10 or 7 out of 10. There's some number where when they reach that number, let's say it's 6 out of 10, they get right. Somebody at Amazon says, we're so good at predicting what they want. Why are we waiting for them to order it? Let's just ship it. And so just go through the thought experiment. As you turn the knob, you get up to some level where Amazon says, let's not wait anymore, let's just ship it. So let's say they ship you a box of stuff, and the box arrives, you open it, and you take out the things you want. So let's say you want 6 out of the 10 things, and you leave 4. And you might say, well, wait a minute, why would they ship you things if they know that you're not going to take all of them, you're only going to take 6 and return 4? From their perspective, they are potentially significantly increasing their share of wallet. So whereas they might have sold you 2 of those things, and you might have bought 4 of those other things from their competitors, either online or offline, now they're selling you all those 6. And maybe you would have only bought 5 of them. And the 6th one is something you kind of wanted, but not really. But now that it's right on your doorstep, you think, I might as well keep it. Furthermore, now you've put 4 things back on your porch in the box, the things that you didn't want, and now Amazon, it's in their self-interest to invest in a fleet of trucks that are going to drive down your street once a week and pick up all the things that they deliver to you and your neighbors that you didn't want in order to lower their cost of handling the returns. Now, I'm not sure whether Amazon will ever do this. It's not like they've never thought of it. This is a patent they filed on an approach they called anticipatory shipping, and they've already started testing it in some markets with clothes. Okay, so just with clothing items in some markets. But the point here is that the thought experiment is very powerful. The thought experiment is what happens. Remember, the only parameter we moved was turning the knob. And what's so interesting about turning the knob is that as you turn the knob, it's like nothing happens, nothing happens, nothing happens. In other words, we see it's getting a little bit better in terms of recommending stuff as we're shopping, but we don't even really notice. Nothing happens, nothing happens, nothing happens, and then it hits some threshold where all of a sudden everything changes. They change the entire model from shopping, then shipping, to shipping, then shopping. We shop on our front porch instead of on the website. And they vertically integrate into a fleet of trucks and so on. And you can go through that thought exercise with imagine if you could predict insurance claims or bank loans or acceptances into MBA programs. If you could crank that knob up to a certain length, there's some number where you cross the threshold and it creates opportunities for a completely different approach. A so-called disruption. Okay, so when Google announced last year that they were moving from a mobile-first strategy to an AI-first strategy, is that just marketing or does it mean something? It means something. So when they said before they were mobile-first, what mobile-first meant is not just they want to be good at mobile, everybody wants to be good at mobile. Mobile-first means that they will be mobile at the expense of other stuff. In other words, they will sacrifice their website and physical stores or whatever in order to be mobile-first. That's their number one priority. So what does it mean to be AI-first? It means putting that dial at the very top of your strategy priorities. It means that's your number one priority. That you will trade off other things. In the case of Google, they will trade off short-term user experience. They will trade off revenues. They will trade off privacy in order to crank the dial. When asked this question on Quora, what does it mean for Google to be AI first? Peter Norvig, who's the research director, responded. And the essence is down at the bottom. He says, with information retrieval, that's when we do a query on the Google site, with information retrieval, anything over 80% recall and precision is pretty good. Not every suggestion has to be perfect, since the user can ignore bad suggestions. With assistance, there's a much higher barrier. You wouldn't use a service that booked the wrong reservation 20% of the time, or even 2% of the time. So an assistant needs to be much more accurate, and thus more intelligent, more aware of the situation. That's what we call AI first. So from a computer scientist perspective, that's how he defines AI first. From an economics perspective, we would add to that the trade-off. When you make AI first, you make other things second and third and fourth. And so they're putting this as the priority, turning the knob. One example of making it a priority is reshuffling the deck. Moving people who are outside the CEO's office somewhere else and moving the people who are working on AI right in the same office as the CEO. So a year ago, the Google Brain team of mathematicians, coders, and hardware engineers sat in a small office building on the other side of the company's campus. But over the past few months, it switched buildings and now works right beside the lounge-like area where the CEO and other top executives work. Okay, so to conclude here, when people come to our lab what we notice is this dissonance. And the dissonance is they arrive at the lab and they say, I get it, I get the Amazon recommendation engine and Siri. Remember, Siri is just a prediction machine. Siri doesn't understand what you say when you're speaking into Siri. Siri hears an audio signal and predicts the vector of words that you're saying and then predicts the response that you want from what you said. And so people say, I get it, these are very clever, they're amazing, but they're not transformational. These are not transforming any business or any economy. But on the other hand, this is a chart of venture capital into AI, a very steep curve. In the last 2 quarters of the Obama administration, the White House released 4 reports on how to prepare the American economy for what was coming around the corner with AI. As far as we know, as what we can find, it's the only technology where the White House has released 4 reports in 2 quarters since the Second World War. Then there was the Google announcement, followed by a series of other companies announcing moving to an AI-first strategy. Then last July, the government of China announcing their strategy, incredible amount of resources to compete in AI, and with the goal of by 2020 catching up in some fields of AI, by 2025 dominating in a few subfields of AI, and by 2030 dominating across every field in AI was the aspiration. Then in September, the president of Russia announcing AI is the future, not just for Russia, but for all of humankind, and the country that leads in AI will rule the world. Then later on in that month, we hosted at Toronto what I think is still the greatest gathering of economists to meet on the economics of AI. So the former Treasury Secretary Larry Summers, the former chair of President Obama's Council of Economic Advisors, Austin Goolsbee, the chief economist of Google, Hal Varian, the chief economist of Microsoft, Susan Athey, Professor Danny Kahneman, a Nobel laureate, and others gathered to talk about the economics of AI, because computer science had gotten so far ahead of economics on this subject. At the end of the meeting, Danny Kahneman, who's the author of the Thinking Fast and Slow, concluded with this. He said, I want to end on a story. A well-known novelist wrote to me some time ago that he's planning a novel. The novel is about a love triangle between 2 humans and a robot. And what he wanted to know is, how would the robot be different from the people? I propose 3 main differences. One is obvious. The robot will be much better at statistical reasoning. The second is that the robot would have a much higher emotional intelligence. So we think of us as being, we'll always be better than machines in emotional intelligence. Professor Kahneman says, no, not so. AIs are already better in some domains. They're better at detecting minor facial changes to detect changes in moods. They're better at detecting minor changes in audio to detect when someone's voice is reflecting that they're getting happier or sadder or angry or jealous. The third is that the robot would be wiser. Wisdom is breadth. Wisdom is not having too narrow a view. That is the essence of wisdom. It's broad framing. A robot will be endowed with broad framing. When it has learned enough, it will be wiser than we people, because we do not have a broad frame. We are narrow thinkers, we are noisy thinkers, and it is very easy to improve upon us. I do not think that there is very much that we can do that computers will not eventually learn to do. So, on the one hand, we have these things these AIs that we see that look neat, but they're not transformational. They're not disrupting industries. And on the other hand, we have all these learned people and powerful people who are making claims implying that AI is going to have this spectacular effect on the economy. How do we reconcile these 2 things? And in our view, the single thing that reconciles these is time. It is having a thesis on time. That the dial in most applications is sitting there at a 2 out of 10. And people are working 24/7 on cranking the dial to a 3, to a 4, and it's moving faster in some domains and slower in others. It's not just, in the last time we had a big technological revolution, some companies had a good thesis on time, some had underestimated how fast things would move. In this current revolution, it's not just the Googles and Facebooks and Teslas and Apples. It's also older economy companies that are making bets, as everybody here already knows, companies like GM, John Deere, and so on. We had one company, one of the fellows at the Creative Destruction Lab, built a company in less than a year, less than 20 people, it had virtually no revenues, and was acquired by TD Bank for just over $100 million. And so, to sum up, there was this nice quote that came out not that long ago from Robert Work, who's the former Deputy Secretary of Defense. And he's referring to the race between US and China in AI. and the incredible amount of resources the Chinese government's putting behind winning in this. And he uses the phrase, "This is a Sputnik moment," of course referring to the Soviet launch of the Sputnik satellite, and that kicked off the space race and the creation of NASA and so on. And what I think here, my co-authors and I, is that this is not just a Sputnik moment for defense, it is a Sputnik moment for all of us. That for the people who are right now in the position of leading organizations or running organizations, we get one of these once in a generation. They don't come every year or every few years. It's once in a generation. Something like this comes along that has the kind of potential that this has. For the kids in the audience, I think to a large extent, you will be the ones that will have the creativity of how to really apply prediction machines in ways that the rest of us don't even think of. But the main point here is that, in our view, this creates an opportunity like most of us will never have again in our professional careers. And so for some people that will pose a set of opportunities to seize and pursue. At the same time, of course, there will be challenges. The biggest one will be to make sure that as a society everybody benefits because it has the potential to change a lot of structure socially. That's it. I'll end it there. Thanks very much. So I can take some Nick, questions. Questions? I'm happy to take. Yes, please. Oh, sorry. There's a mic coming, and just because they're recording it. And if you don't mind just introducing yourself.
My name is Elmo. No, I'm Patrick Slattery. My question is, where do you see, if we go back to the one diagram you presented on prediction and judgment and action, do you see a role for innovation in the prediction process itself eventually, or is it something that's more constrained to judgment and action? Well, and if there is a role for for judgment and prediction, will machines be best at doing that, or is that a human complement to prediction?
So can you repeat the first part? I didn't follow what you meant by innovation in prediction.
So if I think of innovation or think of it as creativity, I can see a role for creativity in judgment and in action. Do you see in the long run a role for creativity in prediction?
So I don't, but I might be missing something in the sense that I think of that out in the world in nature, there are probability distributions that describe the phenomena around us, and the AIs will simply be better than we are at understanding what those probability distributions are. So that's not really a matter of creativity, it's a matter of getting higher resolution on understanding the probability distribution. Yes, please.
Hi.
Hi.
Thank you so much. This was super neat. Really enjoy it. Hopefully I'll get to read the book soon. So clearly you're a fan of Danny Kahneman, so I assume that you buy into behavioral economics, right? So that kind of like cuts with, oh, human beings are rational. Maybe they're not. In fact, they definitely aren't. And to me, there's kind of a parallel, and this is where the question comes, like I want to hear kind of your opinion, because to me, right now we make very strong assumptions about AI or deep learning. It's like, okay, if you have enough data, and particularly if it's a vision problem or if it has particular correlations, then boom, you're going to have really good precision and recall, and you're going to have like a magical black box. But my sense is that we are kind of in the rational world. Like these machines, the assumption is we have these like neural nets and we have enough data and boom, it'll work out. And to me, it seems a lot like the classical economics, like this is just going to work out. And I wondered, what were your thoughts around maybe, these neural nets only work a certain way because we have this magical vision data that happens to correlate spatially, and things kind of like correlate spatially and it works properly. And what are your thoughts around, if that's true, then what would be that analogous behavioral economics, and a little more concretely, are we being a little over exuberant about the possibilities around deep learning?
Sure. So I definitely think there's room for being over exuberant in the sense that, first of all, people imagining AIs can do some things other than prediction, where effectively that's all they do. Furthermore, AIs can only really do good predictions where they have good data. And so I think that was part of the other part of your question, is that when you're in domains where we don't have good data, the AIs can't make good predictions. The one thing I would say is where AIs sometimes feel magical is because they are able to find patterns in data that traditionally we either couldn't use or didn't have access to. So with just the falling cost of sensors, we can censor up so much stuff, image data, audio data. Like in other words, it's not just the lines of data we had in an Excel spreadsheet that we used to use for making predictions of things. We can use so much more multimodal data of all kinds of types that can complement the process of making a prediction. And furthermore, in the old methods, we used to have to, before we started making a prediction, we used to have to create a model in our head of what data we're going to use to predict what outcome. Now we can virtually take a kitchen sink approach where we give it everything and we let the machine figure out what relations, what's related to what to make a prediction. So I think on the one hand, we probably have much more predictive capability than many people realize because of the way the prediction machines work. But on the other hand, they're certainly not a silver bullet. And there's, one of the things that in that first section on prediction is we have a whole section on all the limitations of the types of things that prediction machines are poor at, because they don't have a model, they're basically statistical correlations, and they rely on the underlying data. I'll take 2 more questions, and I know people have to get going, and I'm happy to stick around for offline questions afterwards. Yep.
So in your diagram, you've labeled a whole lot of boxes as complements to prediction or inference, right? And it's clear to me how some of those complementary boxes you could establish monopolies around and extract rents for. But there seems to be absolutely no reason why you should expect that those boxes will be, uniquely retained by human beings, right? Every single one of those boxes is subject to research in a subfield of AI generally. And as they become more valuable relatively, you can expect the research effort to go into them, right? So, a lot of people say everything will be great and human beings, human judgment and so on will become more valuable. But, what reason really do you have to expect that that's true, apart from that it's, comforting?
Okay, so that's a great question. I will attack it with just one example, which is the judgment box. Because in some sense, that's the place where we seem to take the most refuge in, okay, we're safe from the machines because we have judgment and they don't. And so the question was largely, are we just still in the first inning and AI research is moving into these other boxes? So at least in the moment, as long as AI is prediction, that's all it is just prediction. But the point is, if AIs see enough examples of a particular type of judgment, they can learn to predict that judgment. So an example of that is driving. When we're driving, the AI is effectively baking in the prediction of our judgment, so that when we are approaching a yellow light, the AI is inferring our judgment of how whether we're going to step on the gas or step on the brake, depending on whether it's raining and how far we are and from the light and how fast we're going. And our judgment's been baked into to the decision. And so it's true that things today that we call judgment, some of those things AIs will eventually learn to do because they'll get enough examples of us making that judgment in order to predict them. That, I think of this to some extent, like those Russian nesting dolls, that once the AIs are good at predicting a certain type of judgment, we now can focus on a new set of problems, a new type of problems where our judgment is useful in the domain, in that new domain. The question is, at some point, do you run out of nesting dolls and there's nothing left? Your guess is as good as mine, but what I would say is the thing I think that we're very poor at, that our monkey brains are not good at, is in anticipating things we've never seen. So just the same way that if we would have asked people, 200 years ago, when 47% of the population, or even almost 100 years ago, 47% of the population working in agriculture, if we would have said, imagine a world where 45% are no longer in agriculture, they're doing something else, that only like less than 2% of us are working in agriculture. What are those other 45% going to do? Nobody would have raised their hand and said, well, they're going to be at a company called AppNexus, or they're going to be game developers, or they're going to, like, nobody would have done that. Because nobody would have even imagined that such a thing would exist. And I think that's what we're very poor at. We're very poor at imagining that when we have high-fidelity prediction machines, what are all the other things that we could be doing? For example, most people in this room would say, our healthcare systems, no, it's not great, but it's not bad. I think 10 years from now, people will go back and say, I can't believe people were living in those horrible conditions with that terrible healthcare system that they had back in 2018. Because we'll be able to do so much more efficiently, so much more intelligently, because the machines are able to handle a lot of the... And same with space exploration, same with all sorts of things where we feel like we're at the frontier, and in fact, we're just scratching the surface. I'll take one more question and we'll wrap it up. Please.
Vikas from Veris. So my question is around picking problems that we want to subject to AI. Now, I mean, we've dabbled a little bit in looking at deep learning and so on to solve different problems. But there are, of course, lots of constraints. And so is the assumption that no matter what the problem is, that eventually we will be able to turn that dial? Or are there some ways in which we can make better decisions as to what problems to go after and what not to go after?
Yeah, sure. So that's the process of estimating the return on investment for building an AI. So in other words, how long will it take? How much will it cost? How much data do we need to turn the dial far enough for this AI to give us some lift in performance? So in the book, we describe some processes of how to do that. It's I think we go far enough in the book to help people get started, just far enough for non-technical people to get started, to then know when to be able to bring in the technical people to provide more definitive answers in terms of like how much data will we need in order to do this, or what types of sensory information will we need to collect in order to do that. And so there's no single answer to your question, but there is a reasonably step-by-step process for coming up with the answer of where to start and which AIs to focus on first. Okay, great. Thanks very much.